Welcome everyone for the course Introduction to Astronomy and Astrophysics at ISSS BMRF lecture series platform. Today our lecture will be on Sun, and we will cover some basic idea about solar physics, and we will start our lecture shortly from 10:30. This will be the second module of our course, where we will introduce stellar evolution, and the exoplanet. First, we will cover our own star, that is Sun, and then we will cover how the low mass stars and the high mass star evolve along the main sequence. We will learn about the Hertzsprung-Russell diagram, that is popularly known as HR diagram, and see how what is the evolution state of different kind of stars uh, based on their mass, and then we will check how the exoplanets are detected, uh, and what are the different methods of the exoplanet detection. Now we can start the lecture. Okay. Here are some facts about our sun. So the sun is a yellow G-type star. For the stars, we know that there are seven kind of stars based on their temperature and the size. There are OBFGKM, OBAFGKM. Uh, this are the sequence of stars from according to their temperature, and the surface temperature of sun is about 5772 Kelvin. And from the according to surface temperature, sun is a yellow G-type star. About 99% mass of our solar system comes from the sun, and most of the mass of the sun is composed of the hydrogen. So about 91% mass of the sun comes from the due to hydrogen, and this we can call sun as a ball of hydrogen. Sun has huge magnetic field which is generated by the electric currents generated by the flow of hot ionized gas in the sun's convection zone. Near the sun's surface, the magnetic field strength vary so much. Typically, the magnetic field strength is approximately 1 to 100 Gauss, and also the sunspot, the black region or darker colder areas on the sun's surface have the magnetic field of about 3000 Gauss. The magnetic field strength of ISM, or that is the interstellar medium, is about 10 to 100 microgauss. 1 Gauss is equals to 10 to the power minus 4 Tesla, you know. The sun's immense, as the sun is a ball made of hydrogen, it has two kind of uh, force. One is the gravity, which pulls the matter of the sun in the central region, and another is the pressure from the internal pressure, which hold the sun as a object. So the sun's immense gravity tries to contact the sun, but the energy generated by the fusion reaction inside the core of the star pushes the sun outward. So, and this pressure and the gravity equilibrium counterbalance, and the sun becomes stable. Like Earth and other planets, Sun also rotates about its own axis, but uh, its rotation is somewhat unique. It has a differential rotation. Its equatorial moves faster, and the other longitudinal direction moves slower. Sun is the closest astrophysical laboratory that we can study. We can know about what is the plasma conditions of Sun, but and also we can make different models of magnetohydrodynamic and the imaged turbulence, how the Sun becomes trouble, how the Sun emit radiation by studying Sun. Now, the Sun can be split into two regions. One is the interior region and another is the atmosphere region. The interior region is a sphere with the radius of about 700,000 kilometer. 700,000 kilometer is about the interior radius of the Sun's interior. This is made of with three parts. One is core, another is the radiation zone, and another is the convection zone. Outside interior, the Sun, there is an atmosphere which lies on top of interior region and has the following layers such as the photosphere, chromosphere, and the corona. So the Sun can be split into two regions. One is the internal region and another is the external region or the atmospheric region. The internal region has three divisions. One is core, another is the radiation zone, and another is the convection zone. The atmosphere can be differentiated into three other parts. One is the photosphere, another is the chromosphere, and another is the corona. We will see what these regions are special and why they are, what is the main physical process that happens in those regions. So in the internal region, you can see in the right figure that in the core is the most central region. After core there comes radiation zone, and up the radiation zone there is convection zone. Convection zone is the last zone of the interior. And after the convection zone there are three layers. One is the photosphere, which is about 3000 km thick. Most of the Sun's visible light, what we see, originates from this photosphere region. And another top of photosphere, where the region is called the chromosphere, which is about 2000 km thick. We only see this layer and the outer other layers during the eclipse. And the corona extends the outward for more than a solar radius. Surface temperature of the Sun is the surface temperature of the photosphere, that is the first layer of the atmosphere, which is about 5800 Kelvin. So you can see in this figure the different region of Sun. One is the core. Top of the core there is radiation zone, and there after that there is a convection zone. After convection zone, the region is called the first layer of the atmosphere is the photosphere. Then the layer is the chromosphere, and on top of chromosphere the layer is the corona. And the temperature of the Sun, when we say that is the temperature of the photosphere, or that is the most the layer upper to the interior, that is the photosphere, that is about 5800 Kelvin. Now the temperature and the density of the Sun is not constant inside the Sun. Up to the solar radius, the temperature and the density very huge. You can see the temperature of the central temperature is the very huge, that is about 10 to the power 6 into 16 to 10 to the power 6 Kelvin. And this temperature rapidly drops at the solar surface, and the density is also high at the core region or the central portion of the Sun, and the outside the temperature astonishingly drops. Now, so until now we have known that the Sun is made up with the burning, churning gas of hot plasma. The different properties of plasma such as temperature, density create the various layers within the Sun structure. The interior layer of the sun or the interior region of the sun is divided into three regions. One is core, then radiation zone, then is the convection zone. The core is a source of sun's energy. The energy is created through the nuclear fusion. Atoms can travel so much fast that they get collided and fuse together and release energy. Hydrogen atom within the sun fuse together and form helium, and in this process some amount of energy gets released. We receive that energy as the form of heat and light. The temperature of the core is 1500 1500 15,000 15 into 10 to the power 6 Kelvin about. The radiation zone is the zone between the core and the convection zone. This is the second zone of the interior. The radiation zone in the radiation zone, energy moves up and out from the core, traveling as photon. The temperature here is colder than the core. It is about 10 into 10 to the power 6 Kelvin. The convection zone is the last zone of the interior, and convection in here the convection process is happen in which warmer and the less denser matter rises, and the cooler and the less denser cooler and more denser matter sinks. As a result of convection process, the energy in this layer moves up with the warmer plasma and sinks with the colder plasma. Here the temperature is lower than both core and the radiation zone. Here the temperature is about 5 into 10 to the power 6 Kelvin. So at the different region of the sun's interior, the temperature and the density vary so much, and here you can see the temperature is gradually dropping from the core to the sun's convection zone. About 10 to the power 10 Kelvin is the difference of the temperature, and also due to temperature difference the density difference is also there. Now we can see what is the atmospheric structure of the sun. Sun's atmosphere, we have just learned that sun's atmosphere has three parts. One is the photosphere, another is the chromosphere, and on top of that there is a corona. The photosphere is the first layer after the sun's interior or the sun's surface. The photosphere is the visible surface of the sun. This surface turns and churns like a pot of rapidly boiling water. This layer has sunspot. Parts of sun's photosphere surface get interrupted due to intense magnetic field and appear as the blackened spot at the camera when we take image of sun with camera. The temperature in the first layer of the sun's atmosphere dramatically decreases about 6000 Kelvin. So, in the convection zone, the temperature was 10 into 10 to the power 6 Kelvin, and in the photosphere, the temperature becomes just 6000 Kelvin. And the chromosphere is the region which we can call the middle layer of the sun's atmosphere. Here the temperature increases from 6000 to 10,000 Kelvin. This layer radiates most of the sun's harmful ultraviolet ray, which is the dangerous and the cancer causing source of energy source in earth. We are protected from this ozone layer in the due to earth's atmosphere, or the ozone layer protects us from the UV rays. And the last layer of the sun's atmosphere is the corona. This is the outmost layer of sun's atmosphere. It extends some millions of kilometers above the sun's visible surface. It contains large outer envelope of extremely high temperature and the low density gas. The temperature here drastically increases about 10 to the power 6 Kelvin. About 10 to the power 6 Kelvin. So until now, we have learnt about the structure of the sun. So the structure of the sun can be divided into two parts. One is the interior of the sun, another is the atmosphere of the sun. So in the interior of the sun, there are three regions. One is the core, that is internal region where the hydrogen fusion is happening. hydrogen atoms get fused and form the helium atom. And in this process, the amount of energy is radiated, and then after the core region there is a radiative zone where the radiation, where the temperature drops from the core about 10 to the power here the temperature is about 10 to the power 6 Kelvin, 10 into 10 to the power 6 Kelvin, and here the energy moves up and out from the core, and energy travels as the photon. And after the radiation zone, the portion of sun is called the convection zone. The convection zone, here the convection process happens, where of this energy generated from the core moves up with the warmer plasma and sinks with the cooler plasma. Here the photon energy cools down of about 5 into 10 to the power 6 Kelvin in this layer. And after the core, there are three regions of the sun. One is the photosphere, which hosts the sunspot. Another is the chromosphere, from where the UV emission is emitted, and another is the corona, that is extended over millions of kilometers above sun's visible surface. And the photosphere can be called as a rapidly boiling water surface, and parts in the sun's photosphere gets interrupted by the intense magnetic field inside the sun, and some spot of the black spot, that is the intense magnetic field spot or the sunspot, are seen at the photosphere. And in the photosphere is one of the main region of the sun, because here we can see the sunspot. And also here the temperature drastically drops from the 10 to the power 6 into 5 Kelvin, 5 into 10 to the power 6 Kelvin of the convection zone to the photosphere. And then the region is called the chromosphere. Here the temperature starts to increase. Here the temperature is about 10,000 Kelvin. And this chromosphere radiates mainly the UV ray. And the corona is the outmost layer of the sun, which extends millions of kilometers above sun's visible surface. And corona is the large outer envelope of the sun with the extremely high temperature. It has about temperature of 10 to the power 10 into 10 to the power 6 Kelvin, and it holds the low density gas. So now until now we covered the structure of the sun. So now one of the main question in your mind is, why does the sun shine? So the chemical and the gravitational energy sources cannot explain the sun's luminosity. The sun shines because of the gravitational equilibrium keeps its core hot and dense enough to release energy through the nuclear fusion. From inside out, we know that there are layers such as core, radiation zone and convection zone. And in the atmosphere, the photosphere, chromosphere, corona, and sometimes solar wind is also taken as one of the within one of the structure of sun. Four ingredients for understanding the sun as a star and the solar interior is the balance between forces of gravity and the pressure, that is the hydrostatic equilibrium. We have to balance the gravity, that is the internal force, and the pressure due to hydrogen gas, that is the external force. Such balance is called the hydrostatic equilibrium balance. We have to balance the energy produced and radiated away, that is the thermal equilibrium. Nuclear fusion in the stellar core is the source of the energy for sun or the sunlight or stars. We have to understand how the energy is get transported from the core region to the surface. The sun is a self-luminous ball of gas which is held together by its own gravity and powered by the thermonuclear fusion in its core. Now we will look what are the different features or the interesting features of the sun, such as sunspot, solar cycle, solar activity, solar prominences, solar wind. This all at the different region of the sun or the different terms regarding sun. We should know them before. So, what are the sunspots? Sunspots are the temporary cooler region on the sun's surface that are caused by the intense magnetic activity of sun. Sunspots appear dark because they are about 15,000 Kelvin colder than the surrounding photosphere. Photosphere has temperature about 6,000 Kelvin, uh, and it is colder than the sunspot regions are colder than the photosphere. A sunspot can be divided into the two parts. One is the umbra and another is the penumbra. Umbra is the central region of the sunspot, which is about 6,300 degree Fahrenheit or the 3,500 degree Celsius temperature, and the penumbra is the surrounding photosphere, which is about 10,000 degree temperature. Umbra and penumbra at the two region of the sunspot. A sunspot consists of two parts. One is the dark part, that is the umbra, and the brighter part, which is the penumbra, which surrounds the umbra. We have seen that the temperature of the how the temperature of the sun is varies. So the photosphere of the sun is about 6,000 Kelvin. Chromosphere of the sun, at the chromosphere the temperature increases. There is a small increase of temperature, and in the corona, then atmosphere, there is multiple order of 10 to the power 4 to 10 to the power 6, that order of 10 to the power 100 orders of increase of the temperature. Now we know that the umbra is the temperature, it's the central region, which is the central dark part of the sunspot, and it has about temperature of 3,500 degrees Celsius, and the penumbra is the surrounding, which has temperature of about 10,000 degree Fahrenheit or 5,500 degrees Celsius, 5,500 degrees Celsius. Yes, okay. Penumbra. Yes, the photosphere temperature is about 6,000 Kelvin. The penumbra temperature is the surrounding photosphere, which is about 6,000 Kelvin temperature. The number of sunspots on the face of sun varies within an 11-year period, that is called the sunspot cycle. Solar minimum and the solar maximum, these are the two terms you often seen about the sunspot. Solar minimum is the period in the 11-year solar cycle when sunspot activity is its lowest. During this phase, the sun's magnetic field becomes more stable, and we see fewer number of solar flares and the coronal mass ejections. We will see these two terms, that is the solar flare and the coronal mass ejections, in the upcoming slide. And as for now, you can take that solar minimum is the phase when this number of sunspot is minimum in the solar cycle, and the solar maxima is the phase where the sunspot number peaks or the reaches at the highest number. And it has been seen that the solar storm or the solar flare or the coronal mass ejection events is largely correlated with the solar minimum and the maximum. So when this is solar maximum, you see many sunspot and also see the stronger auroras, stronger solar flares, and the potential, and due to those, some potential disruption of satellites also happens. Sunspot appear darker than their surrounding because they are the cooler region of the sun's surface caused by the magnetic activity of sun. However, they can become brighter when they are associated with solar flare or the coronal mass ejection. During these events, energy is temporarily released in the and increase the brightness of area around the sunspot. In the terms of solar cycle, sunspots are the most numerous and can appear brighter in the vicinity during the peak of their solar cycle, which is occurred approximately in every 11 years. At the solar maxima, sunspot activity is heightened, leading to more frequent solar flares and increased overall brightness in the certain region of the sun. So, why does sunspot form? The sunspot cycle, such sunspot cycle results from the winding and the twisting of the sun's magnetic field due to the differential rotation of the sun. The sun rotation speed is not same in the along the equator. Lower altitude rotate faster than the higher altitude. So, as a result, the magnetic field lines wind up in the sun and like the rubber band, and a different kind of solar sunspot or the sunspot structures get formed. So, you can think this as a example of that. The first, there was a poloidal kind of magnetic field in the sun. So, in this poloidal kind of magnetic field, the equator is rotating faster. This kind of magnetic field you can consider as a rubber band. So, as this equator is rotating faster, this will be stretched more. The rubber band in the equator region will be stretched more. So, there will be the rotation will be winding up. The rubber band will be winding up along the sun's surface and create different kind of magnetic field structure. So, this kind of poloidal to toroidal magnetic field and the toroidal to the poloidal magnetic field transformation is the main cause of the sunspot solar cycle. Sunspot number varies as per latitude, has a strong latitude dependence. So, in the latitude dependence means you can see the sunspot tend to appear in the bands between 30 degree north to 30 degrees southern latitude during the solar cycle, moving towards the equator as the cycle progresses. In the solar maximum, you can mainly see this sunspot at about 30 degree north to 30 degree south, and when there is a solar minimum, the sunspot number decreases, and also you mainly see the sunspot near to equator, that is the 0 degree latitude. This kind of observation is termed as the Sporer's law, and this is one of the main feature of the sunspot. The latitude of the sunspots rises and falls in 11-year cycle. At the sunspot minimum, spot begin at latitude 30 to 40 degree. As the cycle progresses, the spots appear at the lower altitude. So, you can, the yearly plot of the latitude, sun's latitude is and the solar activity creates one of the diagram that is known as the butterfly diagram. So, solar activity including the solar flare, prominence eruptions and the coronal mass ejection, solar energetic particle events and the high-speed solar wind streams from coronal holes vary frequently with the solar cycle. Suppose in the 2001 there was the maxima. Yes, 1996 there was a minima, solar cycle minima. So, when there was a maxima, you can see the sunspot begin to is appearing at the 30 degree north to 30 degree south at this latitude. And in the 2001 there was a maxima, and in the 2002 the sunspot number you can see is decreasing, and then in 2006 the sunspot number decreases and it goes to the solar minima. So now this show the cycle 23, and the cycle 23, here the number of sunspots has been plotted with the year. You can see there is the peak of the sunspot number, and then there is a drop of sunspot number. And same thing happened for another 11-year cycle, that is the cycle 24. Here also sunspot number increases and then decreases. Yes, the sunspot number, the maxima is not the same for every cycle. The maxima also varies. That is due to, maybe that is the scope of the research, why this sunspot number is not same in all the cycle, and do the internal structure of the sun or the magnetohydrodynamic activity decide the what will be the number of the sunspot in different cycle. So the people who try to predict what will be the cycle, the maximum number of sunspot in the next cycle, they usually use the data from the previous cycle sunspot number and different magnetohydrodynamic model simulation to predict the sunspot number in the next cycle. And this kind of prediction is can tell us what will be the number of coronal mass ejection, what will be the number of flares from the sun in the next cycle, and based on that, the general the space satellites are put on the orbit, because in the 2025 there is also a cycle, and as this is a very old figure, and you cannot see that cycle 25 here. So today we are just introducing what is the sunspot number, what is the sunspot, what are different facts about the sunspot. So we are not discussing any of the thing why that happens. That thing is beyond our scope. So until now we discussed few facts about the sun, that the sun is made of about 91% of sun's mass comes from the hydrogen. So you can call sun as a ball of hydrogen, and in the sun is supported by the hydrostatic pressure equilibrium, that is the pressure due to gravity and pressure due to the gas. Also we know about the sun different region, that are the sun's interior and the atmosphere. Interior, there are three parts. One is the core, then is the radiation zone, and another is the convection zone. In the core, the fusion process happens. In the radiation zone, the energy or the photons generated from the core moves up, and the convection zone, the energy rises with the flow of plasma. And here the convection happens when the less dense plasma or the cooler plasma sinks, and the more temperature plasma and more density plasma rises up. And the temperature here is about 10 to the power 6 Kelvin, 15 to 10 to the power 6 Kelvin at the core. At the radiation zone, it drops to 10 into 10 to the power 6 Kelvin, and about in the convection zone, it is about 5 into 10 to the power 6 Kelvin. And sun's atmosphere is at this three layer. One is the photosphere, another is the chromosphere, another is the corona. In the photosphere, the temperature is above 6000 Kelvin, and here this layer holds the sunspots, and the chromosphere is the next layer from where the UV photons get emitted, and this layer has some small rise of temperature, that is, it is the temperature of 10 to the power 4 Kelvin, about 10,000 Kelvin. In the corona, the temperature is about 10 to the power 6 Kelvin. There is a huge rise of temperature between the chromosphere and the corona. You can see here is the temperature is 10 to the power 4, and here is the 10 to the power 6. About 100 times of temperature increase happens in the chromosphere, between chromosphere and the corona. and we do not exactly have any idea why the chromosphere and the corona have this kind of high temperature difference. There are different model of the why corona has high temperature, why corona what process, physical process is contributing of such high temperature. But the exact idea, the exact model, there are different model and every model has a drawback kind of thing. So why does the sun shine? So in the sun shines because of the gravitational equilibrium keeps this core hot and dense enough, and the energy gets released at the released due to the nuclear fusion. And the sun is a self-luminous ball of gas held together by own gravity and the powered by the thermonuclear fusion in its core. We learned about the sunspot, which at the cooler region on the sun's surface. Uh, in the sunspot have the temperature of about the internal region, that is the umbra. This has the sunspot has umbra has temperature about 3500 Kelvin, and the penumbra, that is the outer region of the sunspot, it has temperature of about 6000 Kelvin. That is the temperature of the photosphere. The number of sunspot vary. The number of the sunspot appear. The sunspot has the huge magnetic uh, form due to the magnetic activity of the sun. This period, the solar minimum, the sunspot number decreases, and the sunspot which we will see, that is along the 0 degree latitude, and the solar maxima, the sunspot number is high, and we generally see at that time either in the 30 degree north or 30 degree south latitude, and just like a band kind of thing. Sunspot appear darker than the surrounding area because they are the cooler regions of the sun's surface and surface, and sometimes sunspots are become brighter and they emit some of the mass of the sun. That phenomena is known as the coronal mass ejection, and during those kind of event, the energy released can temporarily increase the brightness of the sunspot area. um, and the umbra, penumbra, this kind of so the very huge brightness. So the sunspot cycle results from the winding and the twisting of the sun's magnetic field. There is a toroidal to toroidal and a toroidal to poroidal kind of magnetic field transformation that happens due to differential rotation of the sun. Differential rotation means the low latitudes rotate faster and the higher latitude rotates slower. And also there, and if you plot the sunspots as a year, you can see when a diagram like the butterfly wings, and this kind of diagram is known as the butterfly diagram. And number of sunspot varies with year. You can plot that you will know just like a cyclic kind of plot, low high low high low, that kind of plot, and but the highest point would not be seen for each cycle. So how does the solar activity vary with time? The number of sunspots rises and falls in the 11-year cycle. As the sunspot number rises and falls, the frequency of prominence, flare on the CME activity also changes. Number of sunspot varies in each cycle. Here is another such kind of plot from the previous figure. Previous figure show the plots from the cycle 12, 13, 24, and here is the other previous cycles has been shown. Now we will learn about what is the solar wind. Solar wind is a stream of charged particle that is constantly being emitted from the sun in the all direction of the solar system. This helps the planets from their magnetic field and also gives comet tail. So the surface of the sun shakes its own magnetic field, launches wave into the millions degree Celsius corona. At this point, magnetic field lines are like the ropes when you tie a rope uh, in two pole and shake. You can see that the rope pattern gets changes, and you can think of the magnetic field line of sun by that way. In the corona, some of these lines are reflected and begin to interact with those that are traveling upward. This interaction creates turbulence that forces the magnetic field to change directions abruptly, and this turbulence changes the direction and generates energy and heat. And at the last, this continues to happen in the solar wind as they spread out towards Earth and keeps them hot. So solar winds are the stream of charged particle that is constantly being emitted from the sun in the all direction of our solar system. Due to the solar wind, it is believed that the sun, our Earth's magnetic field and the field persist, and also solar wind is the main cause of the comet tail. As we discussed, the sun releases a constant stream of particles and magnetic field that is called solar wind. The solar wind slams worlds across the solar system with the particles and radiation which can stream all the way of planetary surfaces unless they are altered by the atmosphere and the magnetic field or both. Here, how these solar particles interact with few selected planets and other selected bodies has been discussed. So, as we know, the comets have a sort of atmosphere that is known as coma. It is created as the comet's frozen ices turn into gas by sunset. Sometimes of these gas particles become charged in the intense sunlight. Once that happens, they move in the concert with the magnetized solar wind and forming that at what we see as a comet's tail. So the cometary tail is formed due to the charged particle generated by sun, and also for the planet such as our Earth, Jupiter or Mars, the solar wind has a huge effect. Solar wind is the mostly deflected by our Earth's magnetic field, but sometimes when intense, it can leak through. Once near Earth space, the particles can trigger auroras near the pole. And the moon and the sun for the sun solar wind for the Earth, solar wind create aurora in the higher latitude, and the moon is because the atmosphere of the moon is so thin, the solar wind hits the moon's surface directly with just a little bit of deflection by a small bubbles of the magnetic field scattered across the surface. This bombardment deposits ingredient that could make water. And for Mars, when the solar wind crashes into Mars' atmosphere, all the energy creates a layer of electrified particle that is called the anopause, which in turn also helps to shield the surface from the solar wind. And Jupiter's magnetic field is similar to Earth, but much larger. That is, the magnetic field creates a bubble that directs the solar wind to stream around the planet. And also the asteroid has no inherent protection around it, so the solar wind can easily batter their surface. The incoming particles sometimes kick the material of their space, changing the fundamental chemistry of what is left on the ground. So the solar wind or the particles or the high speed particles generated by the sun interact with the different bodies of the solar system differently, such as when it interacts with Earth or the Jupiter, its direction gets deflected. So this solar wind particles are generated from the sun. They travel. If they encounter the earth, which has the magnetic field line, its path gets the path of the particles gets reflected, and either it goes to it moves around the planet, or one another thing, if it get deflected such a way that it gives the earth's pole, it create aurora kind of thing. In the earth and the Jupiter, such deflection of the charged particle happen. But for the Mars, the solar wind crashes in the Mars atmosphere, and all its energy is create a layer of the ionosphere, which help to shield the planet from the solar wind. This happens because the Mars has lower magnetic field than the Earth and Jupiter. And for the comet, this kind of solar wind create a comet at its tail around the comet. And for asteroid, the solar wind bombard the surface because the asteroid have no inherent atmosphere kind of thing. So the material, it changes the fundamental properties of the material in the asteroid. So due to solar wind, the solar system objects are get affected differently. So when you encounter some object in the solar system, you have to keep mind how if it has atmosphere, if it has magnetic field, so that the solar wind particles interacted with it or not. So this up to this was the solar wind. And what are the solar prominences? We learnt about this terms very much. And gaseous from the, so what are they? The solar prominences are the gases from the corona and the chromosphere that gets trapped in the giant loop of the magnetic activity of sun. This loop is above 100,000 kilometers above the surface, seen for days or even weeks. Solar prominences vary considerably in the size, shape, and the motion, and there are mainly two types, that are the active solar prominences and another is the quiescent solar prominences. Active solar prominences erupt quickly and have lifetimes lasting for several minutes to few hours, and they are associated generally with the sunspot groups, and like this they are correlated with the number of activity with the solar cycle. Sorry, beg my pardon. Quiescent prominences tend to emerge smoothly and subside much more slowly, so that they can be visible for the several months. Solar prominences appear either a flame colored projection when the disk of sun is totally eclipsed, or as a dark ribbon such as the filament. So the solar prominence, the sunspots are the spots where the temperature is cooler than the photosphere. It has temperature of about 2500 Kelvin to in the base of the sunspot. The temperature is about 3500 Kelvin to 4500 Kelvin. At the photosphere, the temperature is about, we know, 6000 Kelvin or 5800 Kelvin. And the solar prominences are the loops of bright gas that is often seen as the connecting two sunspot. And this solar prominences are of two types, that is active sun prominences, that is in for some hours to days, or some few minutes to few hours, you can say. But the quiescent prominences are emerge smoothly, and they remain visible for about several months. Solar flares. What are solar flares? Magnetic field lines from the sun get so twisted that they snap open. This causes solar flares that sends us X-rays and the charged particle. Sometimes sudden and the intense burst of energy from the sun's surface is caused by the release of the magnetic energy stored in the sunspot. This event is known as the solar flare. This kind of eruptions emit radiation across the electromagnetic spectrum. Solar flare can emit radio to X-ray or gamma ray, sometimes erupts the Earth's communication and power grid. Strong solar flares often accompanied by the coronal mass ejection, which can send charged particles towards the Earth and can create aurora and the potential geomagnetic storms. What is coronal mass ejection? The corona, that is the outmost layer of the sun's atmosphere, is only seen at visible wavelength during the solar eclipse. When the light from the stellar photosphere, is blocked. The corona appears bright in the X-ray photos in places where magnetic field traps the hot gas. Coronal mass ejection sent the burst of the energetic charged particle out through the solar system. So, what is the difference between the coronal mass ejection and the solar flare? Coronal mass ejection, commonly known as the CMS, are the large cloud of solar plasma and the embedded magnetic fields that are released into the space after solar eruption. Coronal mass ejections expand as they sweep through the space and often they have the millions of miles across distance, and they can collide with the planetary magnetic field also. When directed at Earth, a CME can produce a geomagnetic disturbances that ignites the bright aurora, short circuit of satellites, and the power grid failure in the Earth. Or in Earth, they can be cause the danger to the space station. The solar flare at the energetic burst of light and particles triggered by the release of magnetic energy of the sun. Flares are by far the most powerful explosions of solar system, with energy released comparable to billions of hydrogen bombs. The energetic particles accelerated in the solar flare nearly at the speed of light, and can travel between the Earth and Sun in less than 20 minutes. Coronal mass ejections and the CME are both ejection of the are both burst of particles from the sun. Until now, we have known that the sun's interior, at the deeper layer of the sun, the weight of at the deeper layer of inside the sun, the weight of outer layer is larger. The sun must have the higher temperature and the pressure dip inside in order to balance the larger weight. The sun's temperature, pressure, and the gas density is largest in the center, and it decreases outward. At the center, the temperature is about 15 into 10 to the power 6 Kelvin, and the pressure is about 10 to the power 11 atomic pressure, and the central density is 15 into 10 to the power 4 kg per meter cube. So, what are the basic physics about the sun? Now we will learn about how the energy of the sun is generated. So the gravity causes all the massive objects to be attracted to each other, we know. For two objects, the force of one object is to move towards one to another according to the Newton's law of gravitation. Macroscopically, one can say there are about 10 to the power 57 hydrogen ions in the sun. All are attracted to each other by the gravity. But an ion is outside. Most of the other ions that is attract to it are towards the center. But if an ion is outside, most of the other ions that attract it towards the center. The sun is a ball of hot gas, mainly of hydrogen, some part of helium also. If one compressed gas, it heats up and its pressure increases. Attraction of outer layers by inner ones toward the center can be balanced by the pressure of inner layers. Then we can achieve the hydrostatic equilibrium. The spherical shape is the equilibrium shape that has least energy in comparison to irregular shape. Like for example, water droplets when the surface tension is balanced by the pressure. So what is the hydrostatic equilibrium? If the particles in the hot gas are in motion, the motion of the gas particle creates a gas pressure that is known as the P. A gas in the bottle exerts an outward force on the wall of the bottle. That is we can write the force, that is the pressure, force, pressure into area, or the pressure is the force per unit area. In the stirred, for the case of stir, there are two forces in the picture. One is the gravity that pulls the gas inward, and another is the gas pressure from below that pushes the gas outward, and gas pressure from the above, that is the pushes the gas inward. The balance between the gravity and the net pressure difference is called the hydrostatic equilibrium. When hydrostatic equilibrium is reached, the star will be stable and its size will be constant. If the hydrostatic equilibrium is broken, it is restored very quickly on the dynamical timescale of 15 minutes for the sun. So, what are the source of solar energy? For computing the source of energy, we have to compute how much energy of a hot ball of gas in its temperature about 10 to the power 6 Kelvin contain. So one atom has energy on average approx kBt. That is when we use the SI unit, one can get 1.4 into 10 to the power minus 20, 10 to the power minus 17 joule. We have 10 to the power 57 number of atoms or the hydrogen atoms inside the sun. So the thermal energy of this number of atom inside the sun will be about 10 to the power 40 joule. Now sun's luminosity we know that is 4 into 10 to the power 26 watt. That much joule per second. So the time, the amount of stored energy in hot gas is enough for time t is equals to, if the sun was only balanced, that is the balanced by the thermal energy or the thermal time scale of the sun, that is 10 to the power 40 by 4 into 10 to the power 26 watt, that is the about 10 to the power 6 years. So the thermal time scale for the sun is too short. We need another source of energy. Nuclear fusion is that source of energy for the sun. In 1905, Einstein showed that mass can be converted to energy by E is equals to mc square. Frederick Aston 1920 measured what is the masses of the hydrogen and helium. Atomic unit, in the atomic unit, the mass of hydrogen is 1.007825 unit. And 4 hydrogen atom has mass of 4.031280 unit. One helium atom has mass of 4.002677 unit. So 4 hydrogen atom, if they fuse and form the helium atom, one can see the 4 hydrogen atom will have a tiny bit massive than the helium atom. Eddington combined discovery of the Aston and Einstein and proposed a new kind of model in 1920. So he told that the sun, inside the sun there is a nuclear fusion reaction where 4 hydrogen combine and 1 helium atom is get created. Every time this reaction happens, some mass is lost and the lost mass is converted to energy. The mass difference is about 4.0312 minus 4.002677 unit, that is about 4.8 into 10 to the power minus 29 kg. And the fraction of the mass lost is 0.007, and the energy is produced is equals to 4.3 10 to the power minus 12 joule. Bethe proposed the following reaction steps, that is called the proton-proton chain, that is the PP chain. Bethe was awarded Nobel Prize for this work in 1967, and the other discovery regarding stellar nucleosynthesis, that is how the elements are produced inside the stars. So the reaction of the proton-proton reaction or the PP chain reactions are like this. There are two hydrogen atom. There are two proton, that is the H1 or the nucleus of regular hydrogen, that is one proton, and this two proton first produces a deuterium, and after the deuterium is getting produced, there are also byproducts in this reaction, that are the photon, that are the neutrino, photon and positron. This kind of reaction has extremely low probability, which defines the slowness of the hydrogen burning in stars, and the stars live so long. And from the deuterium, another proton also gets fused and create helium 3 isotope, and from the helium 3 isotope or from the 2 helium 3 isotope, helium 4 gets created. There is a competition in to the last step. Helium 3 can meet helium 4 rather than helium 3, and helium 3 and helium 4 and action at more hydrogen and get to helium 4 neutron and positron. So this reaction of producing to helium, converting 4 hydrogen to helium, is known as the PP chain reaction. So it is in the kinetic energy of neutrinos and the proton. So what the energy released? It is in the kinetic energy of neutrinos and photons. Whatever the exact sequence of the event, 4 hydrogen, 2 helium, 2 neutrinos and 2 positron, what has appeared to convert to protons and 2 neutrons. So total energy released in synthesizing is 1 helium is 26.73 mega electron volt. Photons scatter efficiently and their energy hit the gas. Neutrinos practically do not interact with anything. They fly through the sun in just 2 seconds, taking their energy away. What energy neutrino may get depends on what the reaction chain they have released when the proton got converted into neutron. In the chain that we considered, neutrinos are created in very first step of synthesizing deuterium. How much energy can they have? We can compute that from the atomic physics relation. So the thermonuclear core, one can check what is the thermonuclear core of the sun. All the reactants are the nuclei of the atoms, which have positive charge, but positive charges repel. The hydrogen nuclei must have very high energy in order to fuse. This requires very high temperature. The only place where the temperature are high enough is in the central position of the sun, that is the that is about 1/4 of the sun's total radius. Even then, it takes on average 10 to the power 10 years for the individual protons to successively meet with other one. Hydrogen burning is very slow. Main sequence star, the sun type star is called the main sequence star. All the main sequence stars have the hot core where hydrogen fusion is ongoing. There are a number of different types of main sequence stars, all based on their size and mass, but they all have similar chemical composition, and the hydrogen fusion is what keeps them in the hydrostatic equilibrium. Transport of energy. The energy generated in the central portion of the sun, that is the core, now transported in the outward. Two methods of energy transport occurred in the sun. One is the radiation, another is the convection. In the radiation method, the photons carry energy from core to the surface at about 70% distance to the surface or to the radiation zone. The photons motion in this radiation zone where the energy transport via the radiation method is the random walk. With each collision, the photon loses energy in this zone. It takes about 1 million years for a photon to travel from the core to surface. And the convection zone is the gas particles move, carrying energy outward. The convection zone is about 30% outer than the sun. Convection cells brings hot gas upwards and the cool gas downward in the circular motion. So how the nuclear fusion happens in the sun, what we discussed, we can just recheck that. In the core sun's core, the temperature is very huge, about 15 into 10 to the power 6, that is the 15 million Kelvin. So the two proton or the hydrogen nuclei are unable to get collide at such high temperature, and nuclear fusion occurs in the core due to strong force overcoming the electromagnetic repulsion force. Very small percentage of particles have enough energy to overcome electromagnetic repulsion barrier and bind together, but there are many particles, so the total energy release is very high. At the lower speed, electromagnetic repulsion between the two hydrogen nuclei, that are the two bare proton, will face repulsion. At the very high speed, the nuclei come close enough for the overcoming the electromagnetic force, and they get bind together, and from they get bind together and can form the deuterium. So the first step, hydrogen fusion by the proton-proton chain, is the first two protons fuse to make a deuterium nucleus, and this step occurs twice in the proton-proton chain. So now there are, in the high temperature of the core, there are two bare hydrogen nuclei, that are the two proton, and they first fuse and forms a deuterium. So this occurred two times, and after the deuterium forms, the deuterium nucleus and another proton fuse and make the helium 3, which have the two protons in the nuclei and nuclear protons and one neutron. This step also occurs twice in the total overall reaction. And from the helium 3 nuclei, two helium 3 nuclei fuse and form the helium 4, and the byproduct of also at the two protons and two neutrons are also formed, releasing excess protons in this process. So the overall reaction is the 4 proton, the 2 gamma ray, neutrino, positron, 2 positron, 2 gamma ray, and 1 helium 4. And this these neutrinos are emitted in the very first step, and this neutrinos and positron is also emitted at the very first step. So in the solar core, there is a thermostat kind of thing which maintains the stability. The core temperature declines when the fusion rate drops, so the core get contracts. because the gravity wins, and as the core gets contract, it heat up, and the core temperature then rises and the fusion reaction starts. So the core temperature expands, fusion rate rise, so the core expands and the cool down. So the solar thermostat maintains the gravitational equilibrium. So until now we discussed about how what process create energy in the sun's core. So we know that in the sun's core the temperature is about 15 into 10 to the power 6 Kelvin. So due to such huge temperature, the proton nuclei can come together and or can get fused. In this, how this reaction happens? This reaction happens due to the pp chain or the proton-proton chain. This proton-proton chain reaction was first hypothesized or the first told by the Bethe, and hydrogen fusion reaction happens where the 4 proton gets converted to 1 helium. 4 proton gets converted to 4th proton or the hydrogen's nuclei. 4 proton or hydrogen nuclei gets converted to 1 helium. So now how this reaction happens? There are 2 proton. The 2 proton gets merged, and in this process there are deuterium nuclei are produced. So in the deuterium nuclei, other than deuterium nuclei, there are also produced the positron and neutron are also produced. 2 deuterium nuclei, so 1 deuterium are produced in here, and every deuterium nuclei get merged with a proton, another proton, and form helium 3. Now 2 helium 3 get merged and produce helium 4. And is this reaction, the electron 2 positrons are the byproduct, and also 2 neutrinos are byproduct. How does the energy from the fusion get out from the sun? The energy gradually leaks out of the radiation zone as the photons randomly collided with the electrons. As they lost energy, the wavelength changes. At about 2 into 10 to the power 6 Kelvin, the gas gets absorbed by the photon. Convection, the gas absorbs the photon. The convection or rising hot gas now transports the energy to the surface. Blobs of photosphere where the hot gas reaches the surface show the bright centers are rising and dark edges are falling, and the photons escape as the sunlight. Now we are near to closing the discussion of the sun. Now we will just see what are the solar missions regarding sun. There are about 20 operating missions with 27 spacecrafts around the sun, and 12 missions are formulation of development, and 6 are under study. And here I am listing some notable missions about the sun. So one of the current mission is the Parker Solar Probe. That is that studies the is an NASA mission and studies the solar corona and the solar wind very closely. Parker Solar Probe is the most closest mission to the sun. And Solar Dynamics Observatory or STO, that is from the 2010 to present, that monitors the sun's magnetic field and the solar activity. Another mission is SOHO, that is one of the oldest mission present. That is a joint NASA-Odisha mission that studies the sun's interior, atmosphere and the solar wind. And IRIS is another mission that is named the Interface Region Imaging Spectrograph that examines sun's lower atmosphere. There are another mission, old mission, that is ACE mission that measures solar wind and the cosmic rays. There is wind mission which study, as the name suggests, to study the solar wind and the interplanetary space. GOES mission, it's a NOAA atmospheric satellites which monitor solar activity and space weather. And solar orbiter SOLO, it is a NASA mission that studies solar poles and the magnetic activity. There are other upcoming solar missions, that are the MUSE mission, that is the investigating solar flares. Helioswarm, that is the studying solar wind turbulence. And the Geospace Dynamics constellation, that is studying the upper Earth atmosphere and the solar magnetosphere coupling. There are other pulse notable mission which generated very wealth of data and wealth of from the sun. That is the Ulysses mission. It was a Russian mission to study sun's polar region. Solar Telestial Relations Observatory, that is the provided the 3D view of sun and the CMS. And another mission is the TRESS mission, which investigated this solar activity on the small field of view, very small field of view. And our ISRO's mission is the Aditya L1 mission, which was which was for the last year, and this here has the 7 payloads here. One is the spacecraft carries 7 scientific payloads for the systematic study of sun. All payloads are indigenously developed in the collaboration with various ISRO centers and the scientific institutes. And the payloads have 7 payloads are different name. One is the VLC. It is for the studying corona, doing the solar imaging, spectropolarimetry and the spectroscopy. And another is the SOOT, that is for the photosphere and the chromosphere study and imaging. And SOLEX is a soft X-ray spectrometer. Hello 1 is the Hertz X-ray spectrometer. And ASPEX is the solar wind or particle analyzer. PAPA is also a solar wind or particle analyzer and in situ measurement. And MAG is for measuring magnetic field. And here is the also a solar info web page. You can just go to, this is a NASA web page. This is Heliophysics Digital Resource Library. Here you can get information about different facility tools. That is the Heliophysics data portal, which is which give you the comprehensive list of NASA heliophysics data resources, and the Helio Viewer. It is a data viewer. It gives the map of the sun obtained by different spacecrafts, and other different tools has been highlighted here. I have given this as a reference. If you can just check the thing. And also, if you are more interested to learn about Aditya L1, you can visit this 2 web page of Aditya L1. Yes. Thank you.